Sir, Professor Shiva sir, welcome back.
Yeah, I'm here.
Yes, sir. Manas.
Yes, sir. Yes,
You
sir.
can start. You can start. Manoj sir is there.
Okay, sir. Thank you, sir. Good morning, one and all. So this is our first session in 5 days FDP, and we have an eminent resource person with us, Dr. Sibake Udgada, to give us a clear picture of the data science applications and challenges. So I would like to call Dr. Manohar Naik, sir, to introduce the resource person. Manohar, sir.
Thank you, Manas. Good morning, one and all. So as Manas told, this is the first session of the 5-day FDP on data science. In midst of us, an eminent professor, uh, uh, Dr. Shiva Kumar Udgata, a professor of computer science at AI Lab and School of Computer and Information Sciences, University of Hyderabad. And the professor Sibake Udgata is a eminent person in various fields. Really, I hope we will be 100% benefited by his lecture and by his talk. And are presently serving as a professor of computer science at the AI Lab, School of Computer and Information Sciences at University of Hyderabad. He also served as a director at Center for Modeling for Simulation and Design, University of Hyderabad between 2012 to 2016. He was a research fellow at International Institute for Software Technology, United Nations University, Macau. His main research interests include wireless communication, IoT and sensor networks, and intelligent algorithms. He has authored more than 150 research papers published in reputed international journals and conferences. He has worked as a principal investigator in many Government of India and other funding agencies, funded research projects mainly for the development of wireless sensor network applications, network security related applications, and applications of swarm intelligence techniques in the cognitive radio network domain. He has worked as a consultant to Tata Steel Limited and Scientific Analysis Wing, DRDO, Government of India. He has been awarded with IBM SUR. SUR stands for Shared University Research Award for Research Project. Mobile and sensor network based disaster management system with emphasis on resource management. He has around 8 edited book volumes published by Springer and also recently co-authored a book titled Internet of Things and Sensor Networks for 19, published by Springer Nature Publication House. And SARS profile, and by seeing SARS profile, SAR is a really eminent, and this talk on the today's first session on data science applications and challenges definitely would be we would definitely, I hope we would be benefited. And with wholeheartedly, I would like to invite Professor Shiba sir to handle this session. Thank you very much. Thank you.
Thank you very much for a nice introduction, and welcome back all the participants. I must thank Central University Kerala for this opportunity. So this talk is being the first talk. I don't want to go into the deep into anything. It's just a overview of data science, the various applications, the various challenges we have. And given this opportunity, I also would like to, and if time permits, I would also like to highlight some of our work which has already been published and some of the work which are currently doing here in our research lab. So please bear with me for another 1.5 hours, and let's see how it goes. So I work for University of Hyderabad. That is the logo of University of Hyderabad, and you all might be knowing that University of Hyderabad is an institute of eminence conferred by Government of India. It's a coveted tag, and we all look forward to delivering because we are expecting around 1,000 crores of funding in the next 5 years, and a lot of labs are being built, a lot of equipments are being purchased, a lot of students are being hired. So it's a good place in India to study, to do research, and to do projects and all these things. So maybe some of you may think of joining University of Hyderabad as research scholars, as students, as faculty members, if you are good at that. So let me move on. So let me start with a prelude. Actually, that's what is currently being said by Jim Baxter, the CEO of Netscape. I think all of you know about the Netscape. The chief executive officer of Netscape said that if you have data, let's look at data. If you all have all your opinions, let's go with mine. What does it mean? It means that whenever we are discussing, suppose now in a board meeting or in a conference or in even in faculty meetings, when we discuss, people say that, do you have anything, any data to support your claim, to support your proposal? If you don't have data, this is only considered as an opinion, right? And these opinions are biased, can be biased opinion, can be unbiased opinion, can be influenced opinion. So people say that if you have only opinions and that doesn't support it by data, then let's go with mine. Let's better you start with mine only, and it's my opinion. But if you have data, I'm ready to change myself. I'm ready to do the course corrections. So what does it say? He says that if you have data, let us look at the data and take a decision. If you all have opinions, I will have mine opinion, and that prevails. So that's the prelude with the data and why data is important. I'm talking about that anything you talk about today, unless it is backed up, unless it is supported, unless it is substantiated with data, it doesn't matter. It doesn't mean anything, right? So we all know that data is all around. You look around, you have data. So lots of data is being collected and warehoused. Warehouse means data warehousing is basically data storing in a particular format. So scientific experiments generate data. We all do scientific experiments and we collect a lot of data. Internet of Things, which is basically a network of sensors, and we do a lot of work on that. So a network of sensors collect gigabytes of data, zillions of data, right? Web data, when you browse web, e-commerce, Amazon collects gigabytes of data, Flipkart collects so much of data, everybody collects data. Financial transactions, whenever you purchase something, whenever you look at something, all these things, all these things are basically generating data. And the last one, social network, right? Your Facebook generates lots of data, WhatsApp generates lots of data, Twitter generates lots of data. So data is all around, whether you like it or not. You are in the sea of data. You are completely surrounded by the data. So next couple of slides, I will show you some images which are actually meant for collecting data. Look at who is collecting data, who is not collecting data. After this set of slides, you will see that who is not collecting data. Everybody is collecting data. Whatever you are doing in the internet is basically a data collection mechanism. And as far as the theorem goes, nothing is free in the internet, right? The principle is that nothing is free in the internet. Everything looks like free in the internet, but in the disguise of free, they are collecting data. They are collecting about your personal profile. They are collecting about your browsing habits. They are collecting about your preferences, and then they take decision which helps them in their business. So what is collecting data? All your browsers are collecting data. All your search engines are collecting data. Just to give you an example, suppose you write a mail to one of your friends that tomorrow you are coming to Hyderabad by such and such flight. And the moment you type your mail and send it, you see that there are a lot of pop-ups that are coming up. Cheap hotels in Hyderabad, cheap flights to Hyderabad, destinations in Hyderabad, hotels in Hyderabad. How does it happen? Because the Google search engine collects all those data, searches all and parses your mail, finds out the keywords, and then suggests you, recommends you certain things actually. So everybody, Microsoft's Bing is collecting data, Yahoo is collecting data, Ask.com is collecting data, all your browsers, Firefox, Chrome, Internet Explorer, all of them are collecting data. Your smartphones are collecting data, your tablets, your tabs are collecting data, your laptops are collecting data. Your gaming devices, your Xbox, your all your gaming. When the kids play game, what are the games they are playing? How they are playing? How good they are playing? Everything is collecting data. Just look at these things. This Netflix is collecting data, your movie preferences, your movie watch pattern, your how much time you spend on a particular movie, how much time you are spending on a particular serial. Everything is data is being collected, and accordingly the preferences, accordingly the recommendations are decided, and accordingly the web series are being made. It's not that those web series are only recommended depending on the user preference, because it keeps changing, right, over a period of time. And depending on the preferences, etc., they keep changing their recommendations, they keep changing their designs, they keep changing their movies, the way the movies are built, etc. So everybody is collecting data. Look at this. Hospitals are collecting data. Your laboratory reports, your pharmacies, your what do you call, your medicine buying habits. What are the medicines you are buying? And if you today you go and buy a medicine, let's say some medicine, let's say paracetamol and other things. So tomorrow you get something, if you have taken paracetamol, you should take this tonic because you are a little bit weak and other things. How is it possible? Because they are all collecting data. Your imaging, right? You take an ultrasound image, you go to a medical, you go to a hospital, everything is being collected as a data. So in the process, what happens? Zillions, gigabytes, petabytes, and all these things, I mean, whatever bytes you are collecting data, and they are being stored in a distributed manner. Now, what you do with this data is very important, right? So everybody is collecting data. Government agencies are collecting data. Pharmaceutical companies are collecting data. Pfizer is collecting data about your profile, your I mean, if you are suffering from diabetic or you are suffering from blood pressure, everything is collecting data, and all those data are being put into some servers, put into some cloud, where the decisions, when somebody, the big boss, is watching there. So everything, I'm just showing the pictures here. Everything is collecting data. And your credit card, the way you spend your credit card, right? Your spending pattern on what are the things you're buying, where you have bought it, what you have bought, all these things are being done. I can tell you a small example actually. Now look at this. Suppose you are flying in a airplane, right? Now Google knows that you are flying in which plane, which time, when you are going to stay, where are you going to stay, who else are flying in that particular plane, etc. How? Because when you book a ticket, a copy of that ticket comes to your email, and that copy of that email is being parsed, and all these informations are being retrieved and stored in a particular pattern, so that some analysis can be done on that. All these things. Now so if you look at this, I go back again. If you look at this, all these images say that there are multiple ways of collecting data, and I don't think there is anything that is left here who is not collecting data. So if you are on internet, if you are using a smartphone, if you are using internet data services, etc., it's basically you are contributing to the society in terms of the data. You are a sample. I mean, I'm a sample, because whatever I do, some data is being generated, and that data is being pushed into some cloud, some server, some storage, where I become a sample, right? I'm a data collection sample. Now, once you do collect so much of data, I tell you so much of data. I mean, if you look at your phone, there are so many photos, there are so much of messages, there are so much of information in your small phone itself. Billions of people are there throughout the world, and look at the amount of data that is being collected. And unless you have a scientific way of storing, retrieving, analyzing the data, it means nothing. It can mean so many things, but unless you are structured, scientific in your method, in your approach, you don't get anything. Even today also, if you are not very well organized, there are so many things in your laptop, but you don't know how to retrieve them, because you have not indexed them properly, you have not stored them properly, you have not organized them properly. So we keep searching for something, for example, as family photo, you keep searching for that, but you don't get that easily. So what do you do with the data? You can do some statistical analysis, like online analytic processing, that is OLAP. You can put the data in a warehouse. You know the difference between a warehouse and a database is that in the warehouse you have the time valued or time series data in a particular order that is stored, so that you can do a time series analysis on that actually. As I told you, indexing, searching, and querying. Unless the data is properly indexed, unless you have a better search mechanism, unless you have a proper querying method to query the data and to the data engine and extract the data, you will not be able to use the data the way you want it to be. So there are many types of search, keyword-based search. You type some keywords, like in Google search, you get the data. There is a pattern matching, right? What is a pattern? I don't know the keyword, but I know that he has a large nose, he has a large big eyes, he is fair complexion. So you give some pattern, and then this pattern will be matching with certain data that is already stored there, and the data will be returned. Now, so what do you do with the data? You run statistical analysis. You do some query, because you have to store it in a proper way using indexing, etc. And most importantly, the last two, knowledge discovery and data driven. Now, what is knowledge discovery? When you have data, so much of data, I'm not talking about 1 or 2 or 100 or 200 data items. When you have GTN, I mean gigabytes of data, petabytes of data, etc., you can extract certain knowledge which is not obvious, which is not intuitive. It's counterintuitive. I can give you a small example, right? I mean, sometime back, around 20-25 years back, when we started, and then it was not known as data science. Actually, we were using a little bit of data mining. We call it the data analysis and all that. So University of Hyderabad used to conduct, and today also they are conducting, national level entrance test, and then people from different states or students from different states come and take admission. Now we found one interesting, so we run these algorithms and we found an interesting antidote, I mean interesting information. So we found that in computer science, if a girl has been admitted and taken admission, and then we found that that girl is from a neighboring state called Odisha. So, or putting it the other way, if a girl has taken admission into the computer science department of University of Hyderabad and she is from Orissa, then we found that she is married. So this rule, right? This rule that any girl who comes from Orissa and took admission into the computer science department is married. This was not obvious, right? This is not there in the, I mean, it's not a requirement, right? But it happened so that all these girls who come and take admission into the computer science department were married. Why it is so? Because for obvious social reasons and all that, because the girls who are unmarried at that time, 20-25 years, girls were getting married at an early age. And after marriage only, if the in-laws family are supportive, they go out to read, and good girls come out to read at University of Hyderabad. And that was the scenario. Then what is the importance of this in knowledge? Because this information about this knowledge, when we were planning for the 12th Finance Commission and all these things, then we proposed for a married ladies hostel. In fact, it was not there. When we proposed for the married ladies hostel, we found that there are a lot of students who are coming from different parts of the country, are also married, and they would like to stay in a married hostel. So married research scholar hostel were there, but married PG hostels were not there. So we proposed a married PG hostel based on this knowledge. So many a times what happens when you do this data mining, or you do data analysis on the huge amount of data, you get some knowledge, you get some interesting patterns, you get some interesting information, you discover some interesting information that is hidden inside the data. So that is what is called the data mining or the knowledge discovery part of the data. So once you have the data, huge amount of data, you run statistics on that. You can find mean, median, mode, correlation, regression, distribution. That's what Dr. Rajesh was mentioning in the morning inaugural session. So you can do all these things. You can do indexing, you can do searching, you can find out the data whenever you like it. You can do knowledge discovery because you can run algorithms on top of it and then find out some interesting patterns which is not obvious, which is not seen on the surface of the data. Then the second is that you have data-driven approaches, data-driven analysis. What is predictive analysis? Now look at this. Till the third point, we are discussing about what you can do with the data. You can do some statistical analysis. You can do some searching. You can do some discovery of knowledge. But the fourth parameter, or the fourth pillar is that you can do some predictive analysis. What is predictive analysis? What is going to happen? If this has happened in the past, or if this is the data that is there, what can happen in future? So the prediction analysis or predictive analysis is based on the previous data that we have collected. And if you can do the data probability, that is climate modeling, whether tomorrow it will rain or not, you don't know the amount of data that is being processed to predict the weather for tomorrow, or the predict the weather for the next month, or the predict the weather for the next year. So much of data churning, it requires high performance computing, it requires supercomputers to do the data churning and find out what or predict what is going to happen. So the predictive analytics are also things that you can do with the data. But look, the predictive analytics is future, right? So we don't have future data, but depending on the past, you can predict, you can estimate the future, and that is called the predictive analysis. Deep learning algorithms I just mentioned here. These deep learning algorithms are basically used for predicting the, anyway, my pen is not working. Anyway, good. So the deep learning algorithms are basically a tool, a potential tool, a very powerful tool for doing the predictive analysis. Now next. don't know what happened. Are you able to hear me?
Yes. Yes, sir. Audible, sir. Audible.
But
Yes,
my
sir.
slide,
We can perfectly hear you, sir.
yeah, just a minute. My slides are not changing. I'll have to do something. Just a minute.
Sir, slide title, what to do with the terror?
But I want to go to the other. I'll do the presentation again. Just bear with me. My God. Just a minute. Sometimes these things. Yeah. Sorry. Now it's okay, right? Hello.
Yes, sir. Yes, yes.
Yes, sir. Yes, sir.
Yeah. So this was the last slide. Let me continue. Sorry for the trouble. Actually, my laptop stopped functioning. Yeah. So what is data science? I'll not talk about all these things in detail actually, but I will quickly go through all these things, and in the subsequent sessions you will be discussing all that. So an area that manages, manipulates, extracts, interprets knowledge from the tremendous amount of data, huge amount of data. That is what is data science. And courtesy Wikipedia. So from Wikipedia I picked up some of the definitions. Not exactly that this is the definition, but many people have different views about the data science. But let us stick to this. So an area, that means a scientific way of managing the data, manipulating the data, extracting information, and interpreting the knowledge from huge amount of data is called as data science. The data science is a multidisciplinary field. Don't think that it's only computer science. It is mathematics, it is statistics, it is computer science, it is electronics. There are so many things that are involved in data science. And that is why it is becoming very popular actually. Life sciences, medical sciences, life science, medical science. So many people, so many different fields are using this approach, this science, for their studies, etc. So it's basically a multidisciplinary study. Data science principally applies to all types of data, whether it's large data, small data, multivariate data, multidisciplinary data. All types of data can be used with this. I just continue with this. So the data science says that the theories and techniques from many fields, that means computer science, life sciences, medical, statistics, mathematics, all these things, from many fields and disciplines are used to investigate and analyze a large amount of data to help the decision makers in many industries such as science, engineering, economics, politics, finance, education, and blah, blah, blah. So there are so many, it's almost covers everything. Science, it covers engineering, it covers economics, it covers political science, it covers finances, it covers education and whatnot. So if you look at computer science, these people mostly deal with pattern recognition. As I told you that you discover patterns. There will be some patterns, right? So what is a pattern? The pattern is like, for example, if you have listened to your grandmother and other things, they used to say that if the cloud is dark, very, very dark, it is not going to rain, right? So, if the cloud is noisy, like you listen a lot of thunderstorms and it's very dark, etc., it's not going to rain. So what is this actually? This is a pattern. They have discovered this pattern. They have recognized this pattern over a period of time, over decades, over centuries. And then that knowledge, although it is not very scientific, but that knowledge percolates, goes down to the next generation, etc. So this pattern recognition is that when you have a huge amount of data, the algorithms will discover the patterns inside the data. And that pattern, they will extract the pattern, and that pattern gives you the knowledge. visualization. Lots of different type of graphical tools are there to visualize the data. You can see bar charts, you can see pie charts, you can see ED, exploratory data analytic, and all these things. You require high performance computing, because when you are dealing with a huge amount of data, your normal computers will not be able to, do all these computation, etc. You require different type of databases. So earlier we have learnt about only relational databases, hierarchical databases, etc. But slowly people are talking about, these days, talking about unstructured data, right? So Twitter data is unstructured, Facebook data is unstructured. There is no structure in that data. When you are tweeting something, there is no structure in that actually. So that is why these days this MongoDB has come up, right? MongoDB has become very popular because it deals with unstructured data. It is not dealing with structure. So relational databases or MySQL, or for that matter, your Fox-based database, whatever database, Unify, whatever databases you have worked on, they are basically structured. There is a table, and in the table there are fields, attributes, etc. But what happens when the data is not structured? So that's where the NoSQL has come up, MongoDB has come up, etc. And of course, AI, all these intelligent techniques are there. And all these studies belongs to computer science. So computer science people mostly focus on these things. Mathematical people mostly focus on mathematical modeling of the data, the curve fitting, the least square curve fitting, the principal component analysis, all these mathematical modelings, right? And the linear algebra, right? Data, when you given, it's presented as a matrix, right? So when you deal with the matrix, right, there are a lot of properties with the matrix, eigenvalues, eigenvectors, inversion of matrix, determinant. So many properties of matrix that comes under the linear algebra, and all those things are also part of the data sciences, but that is basically under the mathematical domain. The statistics people talk about statistical and stochastic model. You know, stochastic means randomness. If it's a stochastic process, means there is a randomness in that process actually. It's not quite structured. It's not very disciplined. It's not very structured decision making. There is a stochastic. That means there is a bit of randomness. There is a bit of uncertainty in the data, and that uncertainty has to be modeled, and that is called as a stochastic model. So statistical modeling means finding mean, median, mode, variance, distribution, blah, blah, blah. So all these things are statistical. In the statistical modeling, when you put randomness into that, it becomes stochastic modeling. And then probability theory, right? If this is happening, that is happening, what is the probability that this will happen, that will happen, etc. So we talk about conditional probability. That's where the Bayesian theorems, Bayesian probability, all these things comes into play. Now look at the capabilities of the data and how it moved actually. So I'm picking up this from the Gartner report. Gartner, look at the bottom actually. So the bottom right side of the graph. So Gartner is a Gartner house, and they are very famous for business consultant and all that. So they keep predicting what is going to happen and all that. So Gartner report says that if you look at the graph, look at the difficulty level, right? The difficulty level keeps on increasing in the x-axis, and the value that comes out of the data is keep increasing on the y-axis. Now, initially, when you have simple data, 30-40 years back, we process it, get the information, just to know that what has happened. So basically, you do the descriptive analytics to find out what has happened. Then you go to the diagnostic analytics, right? In the data science, we call it the diagnostic analytics. That's well is why did it happen, right? Then you analyze that actually. And very recently, I think people who are working on AI, etc. Now people are moving from core AI to another branch called as an explainable AI. What is explainable AI or XAI? Explainable AI means you take a decision based on intelligence, based on neural network or whatever AI techniques are there, but you should be able to explain why this decision is being taken. So the decision maker or the business managers or the industries or even the academics or the managers, they want, okay, you give the information, you give the pattern, but they also want to know that why it has happened. Why do you suggest this? So this is called the diagnostic analytics, or you to predict that why it has happened. So first, what happened you can find out from the descriptive analytics. Why did it happen? You can find out from the diagnostic analysis. And the predictive analysis is that if you know what happened, if you know what has happened, then probably you can do the prediction that what is going to happen. That means what will happen. And if you look at this, the red line there, you are almost here, right? We are almost here. We are able to do all these things using the data science technology. And then they call the prescriptive analysis. That means how can you make it happen? That means if you say what will happen, so tomorrow, suppose in a business environment, in a marketing decision or in a recommending decision, let's say in Netflix, they can say that this is going to happen. But if this is going to happen, it is not that it will happen definitely, because you have to do certain things to make it happen. Now it says that that's where the explainable AI comes out, right? It explains that what are the things that is required, what are the things that is important for this to make it happen. So the explainable AI is the future actually, and it requires a lot of optimization, it requires a lot of computation, it requires a lot of analysis, and all these things are the next. So if you look at this, hindsight means what has happened. Insight means to look into what has happened, to look into data to find out what is the reason, why it happened, and all these things. And based on that, you can predict what is going to happen. That is also being done. But then the next is that what are the prescriptions, what are the things to be followed, so that certain things you will make it happen. Because only knowing that it is going to happen is not enough. You have to do certain effort to make it happen. And that is the part, the Gartner says that the next decade will be doing that. Okay. Now this is something called data analytics pillars and foundations, right? If you look at this, why it is important? At the bottom you have data, that's okay. But here, if you see the analytics, it doesn't depend only on technology. There are three things here. One is people, then the process, and then the technology. Now technology, all these machine learning technology, AI technology, statistical technology, tools, etc., they come under one. But the problem with, I think in the morning session also, Dr. Rajesh told that the major problem with the data, in the sense that if you take any tool, you take any statistical tool, you take any MATLAB tool, you take any R package or anything, you throw some data at it, you give some input to it, it will throw back some output, right? So that is the technology. Like it will give you some data input and then output. But that's not enough to take a decision. Data science doesn't stop there. Data analytics doesn't stop there, because any data that goes in, some data will come out, some information will come out, some pattern will come out. But whether that pattern, unless you understand the process, unless you understand the logic behind it, you will not be able to justify the decision. You will not be able to interpret the outputs. So that interpretation of the output, justifying the decision that is giving it, you require some kind of process knowledge. That means the domain knowledge, right? You need to know. Suppose it says that you give this medicine, you do this operation. So that is not enough, because unless you understand the process, the domain of that particular branch of science, you will not be able to take a decision. And third and most important thing is the people involved in that. So data analytics is all about, not only about the technology, it is about the people in the sense we all who are taking decisions, who are making the system run. So don't think that there is a tool, I'll put some data, it will give some output. It will give some output, and that output I will take it blindly. No, the people involved in that has to be consulted. So, okay, let me give you a small example. All of you might have traveled in a plane and might have gone to the airport, right? In the airport, we see that there is an X-ray baggage inspection system, right? You put your baggage and the baggage is scanned. Now, with all this technology, and that is there for 30-40 years or maybe a little more than that, with all this technology, image processing technology, everything, but still the system is not able to take a decision on their own. A lower level police officer or a security officer is sitting with that machine to take the decision. So that's the people. The people there is that the person sitting in the X-ray baggage inspection system, that scanning system, who takes the decision. He asks you to open your bag. He asks you to check what is there, and then he or she is satisfied with the luggage there, and then only it passes through. So that means what? The point which I'm trying to highlight is that the data analytics tool or the data science may throw some outputs at you, but the final decision, the human being has to be involved in that. So the human, that is the people, the process, how it is being done, and then the technology. All the three are the important pillars of the data analytics. Now let me put some scientific computings and here and there. What is the basically, the basic problem. I was talking to one professor long time back. I said that he was trying to tell me that how come a machine is leading a science? For example, computer science, right? Computer is a machine. It's just a machine. He says, look, do you have washing machine science? Do you have refrigerator science? Do you have cycle science? Do you have motorcycle science? Do you have car science? Why do you have a science called computer science? Well, the whole idea is that the computer is much more than a machine. It just evolved like that. Then there is a lot of scientific thing that has gone into that, and that is why it is evolved as a science, an independent branch of science altogether. But if you look at other machines, they have not evolved, or the potential is not that much that it can become a science on their own. Now that was some 20, 30 years back. Now look at this. Now data is becoming a science, like life sciences, like medical sciences, like engineering sciences, like management sciences. Now data is evolving as a science. So that's the importance, that's the focus, that's the potential of data. Now people are trying to say that if this is the case, then whether it is different from scientific computing, like we have been doing scientific computing for decades, how it is different. So now these are some of the differences actually. Now if you look at scientific model, they are basically depends on physics, the law of physics, the law of chemistry, the law of life sciences, the understanding of life sciences based model. So when you make a scientific computing, for example, I want to find out what will be the distance traveling. If you throw a particular, let's say javelin, you throw a javelin with this much of force, with this much of gravitational force, this much of input force, with this angle, with this much of wind speed, this humidity, this temperature, etc., how far it will go. That's a law of physics. So you can do a computing based on that, you can write a formula based on that, and then you can compute what will be the output. So the scientific modeling, maybe there are some 5 integrations, 6 integrations, etc., but there is a formula behind that, there is a model behind that, there is an understanding behind that in terms of physics, chemistry, life sciences, and then you write a program for that and then do the computation. It may require a lot of computation power, but that doesn't mean that it is unscientific. Now it is all based on physics, chemistry, life sciences, the discoveries, the knowledge that we have. The problem is very structured. As I told you, if you throw a particular object, then how far it will go is based on certain theories, certain rules, certain equations. So you use those equations, write the problem in like that. So it's a very structured programming. It's very deterministic. There is no question of and precise, because all these rules, equations, formulas are already there. You have to just code it. Now, because it's huge, so you require a very supercomputer, high-end computing cluster to do the scientific modeling. So what is scientific modeling is basically a knowledge is there, rules are there, formula is there, equations are there, and you are trying to write the program for that. It's very structured, deterministic, precise. There is no question of unstructured. There is no question of randomness. But look at the data-driven approach. When we're looking at the data science kind of a thing, look, I see a lot of data. Now, for example, the example which I've given, right, in University of Hyderabad, we did the data analysis and found that a girl or a lady who comes from a state of Orissa, neighboring state of Orissa, and took admission into computer science department seems to be married. Now, there is no equation, there is no formula, there is nothing there. It's just a pattern. So there is no scientific evidence that why it has happened, right? There is no scientific rule, there is no scientific formula, but it's an inference. It's an inference coming from the data. So the structure is not a problem. These are not structured things actually, because they are not very well-defined things actually. There is no statistical model for that actually. So we don't have statistical models for random. There is a lot of randomness there. There is a lot of unmodeled complexity there. So basically what I try to conclude here in this slide is that scientific models, scientific computing or science as a whole are structured, rule-based, formula-based, model-based completely. But when you come to data, so now what is the next part? I said that, look, I don't know the equation, I don't know the formula, I don't know this, but here are the patterns, here are the data. Now we try to evolve, or we try to develop models, we try to develop equations, we try to develop formula based on the data. Now the difference between scientific and data is that in the scientific, we first develop the model and then we generate the data. In case of data-driven approach, we first get the data, then develop the model, and then develop the equations or formula, etc. So that's the reverse approach actually. Similarly, people say that machine learning is all about data, right? So machine learning is all about data science. Is not true. Yes, machine learning is an important part of data science, but it is not data science. So if you look at machine learning, look at the figure, left side here. It develops new models actually. Machine learning is based on data. It will develop new models, individual models. It will prove that the mathematical properties of the model. How it will prove? You take the data, you develop an equation, you do a principle of least square or something, some equation is there. And then based on that equation, you try to prove that, look, whenever you give this data, this output is coming and it is already there in the data. That's how we test the algorithm over. So this is what is the machine learning part of it. But in data science, if you look at, you on your own, you can also see. In the data science, we don't talk about one model or one individual model, etc. It will explore many models. It's basically a science, right? Machine learning is a technique. But data science is a science. It's a study of data that comes out to be, you explore many models, you look into many data types, you look into many databases, and then you try to see how it works actually. So you will explore many models. Sometimes you build new models, sometimes you tune and hybrid the models. Hybrid in the sense, put 2-3 models together and try to develop another model. You understand the empirical properties. What is empirical properties? Numerical properties, the data properties of the model. We don't understand, I mean, we don't try to understand the physics behind it, or the chemistry behind it, or the life science behind it. We understand the data behavior behind it, right? So what happens in a machine learning? Machine learning is a tool, but data science is a science. It's all about tools. It's about all the tools. It's about all the models. It's about all the understandings that goes into that. So what I do with the prerequisites of a data science, I mean, when you want to do data science research, etc. First, I must say that, I mean, I'm ordered in this order. Unless you have a general aptitude and the skill. What is that I say about the general aptitude and the skill? Say, I cannot be applying a data or a data science model or a data science research without knowing about what it's that I'm going to do, or what is that, where it is going to be applied. For example, people do a lot of research on medical science, etc. But if you see, if you look at good journals about medical sciences, if you look at good publications about medical sciences, etc., you will find one of the author is a medico, one of the author is a doctor in the sense the medico doctor. Why? Because unless there is a medico involved in the development process, you don't understand that medical data. I don't understand the medical data the way I should be. I may read certain things here and there, but they are trained, they are skilled, they are experts. First, in that case, you should have that curiosity. You must have that common sense. The common sense means the domain knowledge about that particular application. And what is that communication skill? I'm not talking about the soft skill here. I'm talking about the communication skill in the sense that how do I communicate that result to the users actually. So this communication is not about soft skill. It's about what graphs you will show, what results you will show, what outputs you will show. So that is called the communication part of it. How do you communicate? Whether it is in a mobile phone, whether it is through a message, whether it is through a mail, whether it is through some alarm. So this is basically the communication skill. So what is the general aptitude and skill I'm talking about? You should be curious. You should have a curiosity about that particular domain where you want to work. You must have some common sense, because I tell you, the final decision, the person involved there will take the final decision about the output of the data. I mean, the usability of the data. So I require a lot of common sense. I require a lot of communication skill. I mean, not soft skill. I require a communication skill to communicate the explanation about the data. For example, I see a pattern, right? I must be able to communicate to the manager or to the boss that this is how it works. And this skill is slightly different from the English speaking skill actually. It's about how do you present the data. Of course, you require a lot of technical skills. You require machine learning models. You require mathematical modeling. You require statistics. You require computing paradigms. For example, Spark, big data, Hadoop, and so many things, right? What kind of computing paradigm? Cloud computing. So you require all types of computing parameter. And most importantly, you require databases, because you have to store the data. So the data can be structured, the data can be unstructured, but you require databases, a lot of knowledge about the databases, querying, indexing, storing, storage, network file system, and all that stuff. So what are the technical skills mostly required for data sciences? You require machine learning algorithms, understanding about machine learning and all that. You require mathematical modeling, eigenvalues, eigenvectors, matrix multiplication, matrix, and all those things. Statistics, distribution, mean, median, mode, regression, variance, all these things. Computing paradigms like big data, Hadoop, R, cloud computing, etc., and databases. And next, what is the data science life cycle we talk about? There is a life cycle involved in the data science actually. So first, and to start with, it requires data discovery. I think in the initial few slides about in my talk here, I've already discussed about the data discovery. From where you get the data? You get it from everywhere. So it involves acquiring data from all the identified internal or external sources. So how do you get the data? You get the data from the logs from the web server. That means what? The browsing history. Google gets the browsing history of everybody, right? So from the web server, if you look at the logs of the web server, you get the browsing history of people who are browsing your web. Data gathered from social media, for example, your Facebook, Twitter, and all these things, they are getting the data. You get data from them. So that is basically a term called crowd sensing. What is crowd sensing? Crowd means people, and what is the difference between a group of people and crowd? The crowd means it's a ill-organized, unspecified, I mean, no objective, there is no specific objective for the people. They have just come together. It's a group of people without any specific objective, without any specific skills, without any it's a heterogeneous group of people. So that's a crowd. And what is sensing? Your sensors are there to sense the data and send it. But here, the sensors are that they will tweet, they will post their idea in the Facebook. So that also gives you some information, some data, and that data is known as the data gathered from the social media. Census databases from the government sources, you can get census databases, right? How many people are there? What is the population of this country? How many people are above this income level? How many are below the BPL, etc. So you get a lot of data from government sources. So this is basically data discovery phase of the data science life cycle, is that collection of data. And I've already told you that how do you collect data? It can come from various sources. One. But once you get the data, you have to prepare the data for the analysis. You have to prepare the data for the to get some inference. What are the data preparation phases? Now, when you collect the data, you will find that there are a lot of inconsistencies in the data. Like, suppose let's say I'll take a review, right? Review of a particular product. Now, what is the review of a particular product? The product is there, and then people have reviewed it. Whosoever purchased, they will review it. Now, you find that many people might not have reviewed it also. And some people, if you are asking for, let's say, 5 parameters, how good is the product look-wise, stability-wise, user-friendly-wise. So you might have given some 5 parameters. Somebody might have filled 3, somebody might have filled 4, somebody might have filled 5, and somebody might not have given any review, etc. So you'll find that there is a lot of places where the data is missing. Now, if you look at sensor data, now you put some rain gauge sensors, temperature sensors, humidity sensors. Because of some reason or other, some data might not have come from some places. So inconsistency in the data is in the raw data is a reality. There will be missing values. There will be blank columns. Some columns are blank. There is nothing there in that column. There will be incorrect data format. You have asked for a particular data format, and that fellow has entered something else in another data format. So all these things are there. So this the process of making the data, prepare the data for analysis, is known as data cleaning. So you need to clean the data. What is meaning of cleaning the data? Cleaning the data means the data has a lot of garbage values, a lot of unwanted values. So the data need to be cleaned. The data need to be prepared. So the first activity of the data preparation is data cleaning. How do I clean the data? Now, how do you clean the data? One is that suppose there is a missing value. Let's say in one column, a lot of values are there, and one particular value is missing. So you can replace that missing value by some kind of an interpolation. That means if the previous value is this, next value is this, you take the average of that and replace that. That is one possible way. The other possible way that remove that record completely. That's another possible way. But there are many techniques. So missing value replacement is one technique, because before analyzing the data, you have to do that. Similarly, blank columns are there. Will you want to remove the column, or what you want to do? Incorrect data format, you have to convert it to a proper data format. For example, date format is there, but that guy has not entered in date format. See, he is supposed to enter the number of the month. For example, 07 for July, 08 for August, but he has entered JULY July, AUGST August. So you have to convert that to number format. So all these things need to be done. That is called the data cleaning operation. Now, so data cleaning is one. What is data reduction? Now look at this. Data reduction is that you have to convert the data, reduce the data. You have so much of data. I might get so much of data about the students, about the people, etc. But for my application, for example, there are some 100 attributes, 100 columns, 100 fields. But for my kind of an application, I need only 4 or 5. So that is called the data reduction. What is data transformation? I don't want to talk about electronics here, but there are a lot of transformation technique, wavelet transformation, Fourier transformation, Laplace transformation. So the transformation is basically transforming one form of the data to the other form. One example, a simple example, what I said is that transforming a month number to month name is a transformation. It's also a transformation. So transformation is required to prepare the data properly, and the data integration. That means from various sources, the data can come, various tables can be formed, and you have to integrate the data to one table or one form so that the analysis can take place. So what is data cleaning? I told you. Data reduction, I told you. Data transformation, I told you. If you are working with electronics people, some people are in electronics, etc. When you get signal, so the time domain signal should be converted to space domain or frequency domain, right? This is a Fourier transform. So those kind of transformations are required. Wavelet transformation is also there. Sorry, just take a glass of water. So all these things are transformation required for right kind of processing and data integration also. And the conclusion is that the cleaner your data, the better your predictions. So the better way you clean it. So one of the important, I repeat, one of the important phases of data science life cycle is data preparation. If you don't prepare your data properly for analysis, you are not going to get it properly. I mean, the results are not proper. Now next stage, so there are 4 phases actually. Data discovery is one phase, data preparation is one phase. Third phase is called the model planning. So the model planning in that case, in this stage, you need to determine the method and techniques to draw the relationship between the input variables, right? So in this case, what happens, there are many input variables are there, right? Temperature is there, humidity is there, so many things are there, right? Now, if there is a relationship between these variables, actually, there will be some inherent relationships, and those inherent relationships can be explored by using exploratory data analytics, by using mean, median, mode, correlation coefficient, regression coefficient, a covariance matrix. So all those statistical techniques are there to determine whether there exists a relationship between the attributes or not. If there is, say for example, if there is a, let's say I have collected the data and there is a direct relationship between column A and column B. That means if I know column A, I can predict column B. So why column B should be there? It should be removed. So in this way, you can find out that what is the relationship between the different data attributes, and how do I do? By using a model planning. So before model planning, you do this kind of analysis to find out what is the relationship between input variables. The most important examples of this is that if you look at this, planning a model is performed by using different statistical formulas and visualization tools like EDA, exploratory data analytics. There are tools available. Python programming, there are tools available. MATLAB, there are tools available. R is a tool for data science only. SAS, Microsoft Access. So all these tools will give you to analyze the data, or to know the behavior of the data, or to find out the relationship between the different attributes of the data. So that will give you a basis for planning your model, like which attributes are important, which attributes are not important, etc. Then finally it comes out to be the model building. What is a model building? The data scientists distribute the data set for training and testing. Okay, I may take a couple of minutes here. The model building is that I have a lot of data. Now what I do is, first I will build a model that I will try to build a formula. I mean, basically building a model means trying to understand the data and prepare a scientific model or a scientific formula or a scientific design for which fits into that data. So what do? We normally separate the data. Suppose I have some 100 data items or 100 data records. I will separate part of the data to be training and part of the data to be testing. So what I do, I divide out of 100 records, I take out 80% of the records, let's say 80% of the record, that is for training. So I will take 80% of the record, give the inputs and try to predict the output. And I continue this process unless the inputs are close to the output. Given this input, I must get the output. So you repeat some iterations and then find out that, okay, my model is good. Now my model is trained that if I give this input, it gives an output which has actually happened. That means your model is trained now. Now you have to test the data. So the 20% what you have taken out, sometimes we call them as validation also. I'll say about that. So the validating the model means the 20% data which you have not used for training will be taken out. And then that will be after the model is completely trained, you give one record from the remaining 20% and predict what is the output and check whether that output has been predicted or that has happened or is the actual output. So the estimated output and actual output is the testing or the validation phase. Now the difference between the validation and testing is that validation means you can do it with the actual data. I mean the 80%, 20%. Testing can be done in future. For example, once this is done, your training is over, you are satisfied with your validation, then you actually deploy it in the actual field and in future you try to test your result. That is called testing. But some people also use it 80% training and 20% testing. That is also done. So this is how you build the model. How do you build the model? Now, what is model planning? You decide what are the attributes you will remain, what are the attributes you will remove, what are the attributes can be fine-tuned, etc. That is it, planning. Building is that case, then once everything is ready, you collected the data, you cleaned the data, you prepared the data, you prepared the model, like what are the attributes, etc. should be there, etc. And then you build the model. So the building the model is like this. You divide the data set into training and testing. Then all these techniques, I mean, I'm not going to talk about technique because I see that the other speakers will be talking about all these things. I'm just trying to introduce what all are this and why you should read this. So technique lies data association, data classification, data clustering. I'll tell you what is classification. Classification means you give a data and try to see that case. For example, in an organization, you have Group A officers and Group B officers. Now, how do you classify them as Group A and Group B? You give all the data attributes and then you find out whether he's a Group A officer or a Group B officer. So this is classification. So once a new employee tells about his or her descriptions, you put that data into the model and the model will say that whether he or she is a Group A officer or a Group B officer. So that's a classification. Association means which data is associated with which type of output. So that's an association. What is clustering? So clustering means, classification means you know that there is a Group A, there is a Group B, there is a Group C, there is a Group D. So if you know the levels beforehand, then it is called a classification. But suppose I don't know the levels beforehand, I only have the data, but I want to group them. Group them in the sense that just group them into different groups. Suppose I say, look, there are so many students are there in a classroom, and I want to do a clustering technique. So in the classroom, if I give these images to the model and I don't know what is that, it will try to say, it will try to classify, okay, these are boys, these are girls. And within the boys, it will try to say boys with specs, boys without specs, girls with specs, girls without specs. And then it will say tall boys, tall girls, short guys, fair guys, fair, white complexion, not white complexion. So these are so what it will do, you are not telling anything. The system will automatically find out that what are the groups that can happen, and they will try to classify them, group them. And the new entry or the new record or the new data that comes in, it will automatically go to a particular group, so that you know that this data, this record belongs to this group. So most common data science modeling tasks are, I think these are the following. Classification, as I told you, what is classification? You try to level, the levels are there, and then you try to classify them so that the new record, new data, new sample that comes in will decide that which class it belongs to. Scoring, you assign a particular score to the score. Scoring and ranking. Scoring is absolute, ranking is relative, right? First rank, second rank, third rank, fourth rank. Scoring is that how much weight you want to assign to this particular data. Ranking is that in the order of merit or in the order of ascending sequence or descending sequence, what is its position. Clustering, as I told you, it's an unsupervised learning. That means you give the data, it will automatically find out the groups. Finding relationship between the attributes, etc. So these are the common data science modeling tasks. That means classifying, scoring, ranking, clustering, pattern discovery. All the finding relationship is a pattern discovery also. So these are the typical data science algorithms, data science tasks. And if you want to know more about it, just write classification techniques. You will find that there are so many classification techniques available. Type clustering techniques, K-means clustering, Hawaiian clustering. There are so many clustering techniques are available. Basically, these are algorithms. But I tell you what to do, whether you go for classification, whether you go for clustering, whether you go for ranking, whether you go for scoring. This depends on the type of people, the person, the human being, the analyst who is sitting there will decide what I have to do. Because you have a data, right? You run all these things, it will give you some information. But whether the informations are useful or not, the person has to take the decision there. And finally, the communication or the output or the dissemination of and interpretation. So some output will come. How do you disseminate that output and how do you interpret that output? That skill is also required. So what is data science life cycle here? Data discovery, that means capturing of the data, data preparation, data model planning, model building, and then output dissemination and interpretation. And if you are not happy with any of these, the cycle repeats. Again, go and collect the data, again do the data preparation, again do the model planning, model building, etc., etc. Now this is another, you don't have to read all these things, but let me tell you, look at the diagram in the below. So any classical research, they call it a T research, T-type research. So T-type research is what? You read the domain and then go deeper into the domain. Go deeper into that particular technique, etc. For example, you are doing machine learning research, read about machine learning a bit, and then go deep into the machine learning techniques, etc. So T research is that little bit of width or breadth, and then a long deep. You dive deep into the domain, into the knowledge, and then find out what is there. But in case of the data science, etc., I picked up this diagram, the data science, etc., it's a pi research. Now, what is pi safe research? Now, look at this. In pi, of course, the breadth is a little more, but there are two depths. Two depth in the sense key. One depth is you look at this actually. One depth is your computing. Like if you are from computer science, you are computing the techniques, or that is one depth. And the other depth is also the domain. For example, if you are doing a data science research in medical domain or medical data, you cannot be only talking about the data, or your research group must be having some people who has the domain depth, domain So more and more you do the data science research on a particular domain, more and more you have to know about that domain also. So this is called pi research. I mean pi safe research and T safe research. So most of the research in classical approach, we are calling it as a T safe research. But these days, new modern research and particularly data science research model is actually pi safe research. Now, some of the statistical techniques, I will just give a small brief overview of this. So some of the statistical techniques for data sciences are linear regression. What is linear regression? Now look at the figure on the right side. There are a lot of blue dots. So these blue dots are actually data samples. Now you have to fit a line in such a way that the distance from the or the perpendicular distance from the points or the data points to the line, if you take the sum of all those things, sum of squared of all these things should be minimum. For example, the black line can be anywhere, right? But if you take the sum of the distance, sum of the squared distance from the black line, a perpendicular distance from the black line to the blue dots, the sum may not be minimum. So if it is minimum, that is called the regression line. So this regression line, what is the advantage of this regression line? That means you are trying to fit a equation, a straight line equation to the data points. And if you want to predict the future, you know the line equation, the equation of the straight line here, just put the values of x, you get the value of y. So that is called a simple regression. If there are two dimensions, y and x. So if x is given, you can predict y by fitting a regression line. But if it is multi-dimensional, that means multiple linear regression. That means if you have x1, x2, x3, x4, and then y, then you have to write w1 x1 plus w2 x2 plus w3 x3 equal to y. So when you get a new x1, x2, x3 value, you multiply it with w1, w2, w3 respectively and get the value of y1. So this is a basic fundamental statistical technique of data science where given the data in multi-dimensional space, you try to predict a linear regression line. It's a simple linear regression line. Now, if you want to make it non-linear, I mean, the line can be linear, the line can be non-linear also. If it is non-linear, so line cannot be non-linear, a curve can be non-linear. So if it's a non-linear curve, we call it a non-linear regression. As simple as that. So we know in statistical techniques, linear regression, simple linear regression, multiple linear regression, non-linear regression, principle of least square curve fitting, all those things are applicable here. There is nothing more than that. Now, what is classification? Now, you see here, you can say that, okay, I can come back. Now, what is linear regression and what is logistic regression? The logistic regression is basically logic, right? True, false. Logic is true, false. So logistic regression says that whether it belongs to this class or that class. That means what? You take a value, you take x1, x2, x3, etc., predict the value of y. Now then you decide a threshold value. That means if the value of y is more than that, it is true. If the value of y is less than that, it is false. That means there are two classes. You are classifying the data, whether it is high class, low class, true class, false class, yes class, no class, higher class, lower class. That means you are classifying it. So this classification is known as logistic regression. So what is regression here? You predict a line, you predict a curve, and that curve, you fit a curve, and that curve, when you put the values of x, you will get the value of y. That is regression. But you are not interested in getting the value of y. You are getting the class of y, to what class it belongs to what level it belongs to. So that is called the logic. So in the logic, you put a threshold value, etc. So then it becomes a logistic regression. So we have decision trees, we have a lot of other techniques that can be classified there. Then sampling, and sampling is very important actually in the sense that we call that as a resampling method also, because say you collect the data from so many people. For example, government collects the data, right? Census data, 130 or maybe 135 crore people are there in India. You cannot be collecting the data. Suppose I want something, some decision to be taken, some planning to be done. Then you say that let us collect the data from 130 crore people. By the time you collect the data from 130 crore people, it will take 5 years or 10 years. And that's not possible. So people call it as sampling. Now, once you have sampling, even if you have data, for example, I have census data, I don't want all these data to come and do the analysis actually. So I will do some sampling. That means I'll choose some randomly, I'll choose some data, create a subset of the data set, and then do the analysis on that. Now, when I do this, every time I run, I pick the samples randomly. That means first time I'll pick some 10% samples randomly, run my analytics. Next time I run, I pick some 10% samples randomly. So the first sample and the second sample need not be same because you are choosing randomly. And then again you run the analysis. Now if you run it 3, 4, 5, 6, 8, 10 times with some 1% sample or 2% sample, and then you try to aggregate your decision and come out with the final conclusion. That is what is called the resampling. So if you look at the original sample or look at the right side of the sample, You look at the original sample, you choose a small subset of that particular sample and do the statistical analysis. That is one. Then similarly, you repeat for 2, 3, 4, 10, 8 to 10 times. And then finally, you define what is the distribution of the sample and what is your result that you are giving. So this is also one method that is very useful in data science. Dimension reduction, I think I didn't want to, this is very, very important in any data science research. In that case, you get data in multi-dimension space. That means 100 dimensions, 100 columns, 200 columns, 300 columns. What happens, suppose I have, let's say I take a student. A student means his name, his date of birth, that means his age, his father's name, his city, from where he has come, his height, his weight, and then how many hours he is studying, then what was his background, that means how good he was in mathematics, what was the mark mathematics, science, and so many things. And then I want to see that what will be I want to predict what will be his grade in the next semester. Now, important. I have a student, I have so much of data about the student, his pocket money, so many things are there actually, right? So you have some 100 attributes about a particular student: height, weight, pocket money, last semester mark in individual papers, and then his father's name, his father's profession, his father's, whatever, his education, his mother's education. So you take some 100 or 200 attributes of a particular student to predict what will be his grade or her grade in the next semester. Now, most important here is that the dimension reduction is that if you take so many attributes and try to predict, many a times those attributes are not very influential, and sometimes they confuse the model also. So it is very important to reduce the dimension of the thing. There are a lot of techniques. One of the most important technique is called the PCA, Principal Component Analysis. Look at the diagram on the next slide. So we have so many attributes, so many colors are the data samples actually. If you convert that 3-dimensional to 2-dimensional, you see in a chessboard kind of a thing, that the data is converted to 2-dimensional. Same data, but is converted to 2-dimensional. That means we ignore the one particular dimension completely. Then you go to the 1-dimension, look at how it looks like in a 1-dimension. What does it mean? It means that any data in any number of dimensions is capable of being reduced to lower dimension space without compromising on the quality of the data for the analysis. Now, I tell you, when you do PCA or the dimension reduction problem, it is important that what is that you are going to predict. Right? If you are going to predict the grades, probably the attributes which are important for predicting grades, marks is important. Then his city name, height, weight, etc. But if you want to predict his sportsmanship, that means what is the chance that he will get a medal in the next tournament, then you have to look at some other parameter dimension actually. So this dimension reduction is that depending on the type of output you are trying to predict, you will reduce the dimension. And that dimension reduction, there are a lot of techniques like Webler dimension reduction, PCA is there, LBF is there, so many dimension reduction techniques are there. And I urge you that you should also read them. And this is very important in form of a data science research. Support vector machine is a classification. I think I can skip this slide. It's a classification technique again. Unsupervised learning, that's what I told you, but I thought we will talk a little more on this actually. So what happens actually, so this is look at the diagram, and the top part of the diagram, there are a lot of people, and those people have a lot of attributes, a lot of data in that. And you give this data, and the model actually tries to classify them, group them into different things. For example, green color, blue color, pink color, red color, it just group them. Now, I didn't say what is unsupervised learning here. Supervised learning means, or supervised data modeling is that you take the data and you also give it a level, the output. Now, input is there, output is there, input is there, output is there. If you have some 1,000 samples or 100,000 samples, out of the 1,000 samples, you try to see that you build a model so that given this input, that output will come. That's called supervised learning. But suppose I don't have any output, I don't know the output, but I just see a group of data, a sea of data, and I want to group them, cluster them, and without knowing what it is. So what the algorithm does is that it looks at the data and tries to group them into different clusters. And that grouping, it depends on the data value itself. It doesn't depend on any level. It doesn't depend on output. It doesn't depend on the user or the programmer, right? So there are techniques like K-means, adaptive resonance theory, ART, Hopfield net. So these are all unsupervised learning algorithms, and you may look at this, or you may be covered in the other talks actually. Now look at some of the applications. What we are trying to talk about is that in data science, one application is that anomaly detection, right? What is anomaly detection? Anomaly detection is that unusual, some unusual pattern is there. You are doing credit card, if I'm working, if I'm using a credit card, every day I go spend some money, etc. Now, sometimes the credit card people call me and say that, okay, look, it seems that you have spent this much of money, and have you done that transaction? Why it is so? Because that's an anomaly that they have detected in my usual pattern of spending, right? So suddenly, if I drive my car at a speed of around, on an average of 50 and 60, and suddenly if I drive at a speed of 100 or 200 kilometers per speed, they find that probably my car is stolen. So suddenly they try to ping me, message me, and say that, are you still driving your car? If you are not driving, they will try to alert the police and all that. So anomaly detection in the data is one important application where a lot of things can be done. So that is one application. Pattern recognition, I think I have already told you the pattern recognition, that you try to find out, discover the patterns, and those patterns will lead to lot of what do you call business decisions, lot of decision makings, so that you can do a better thing actually. For example, here it says that you identify a pattern in the data set is a core data science request. For example, pattern recognition helps retailers and e-commerce companies to spot trends in the customer purchase behavior, right? How you are buying. Now you know the pattern actually. If you buy this, if you buy this, if you buy this, they recognize your pattern of buying and suggest you what you should buy next. So that is a kind of a pattern recognition. Pattern identification, recognition, and suggestions. So these are, Amazon does that, Walmart does that, a lot of people do that actually. Predictive modeling, I think I've already told you that, but I'm just putting it so that these slides can be shared with you. Predictive modeling in the sense that you predict what is going to happen. So that is called the predictive modeling. And in the predictive modeling, we have a lot of machine learning and other algorithmic approaches, linear regression, logistic regression, decision tree. So all these things are used in predictive modeling, so that given this data, what is going to happen? That is what is the predictive modeling. Given this data, what is the output? That's a predictive modeling. So use a predictive maintenance system. For example, now you know that you have a lot of equipments and all these things. You can predict when the machine is going to fail, depending on the behavior, the change in the behavior of the machine. For example, if the vibration, if you have a vibration sensor, the new machine will have less vibration. Slowly the vibration will increase, and you know that if the vibration goes to that level, the machine requires maintenance. That is true with cars, that is true with motorcycles, that is true with high valued equipments and all those things. So predictive maintenance can be done. Similarly, recommendation engine and personalization system, that is very important, because people who are working on recommendation system, it's a huge area of research. Netflix does it very nicely, Hotstar does it very nicely. So lot of people do this actually. What is recommendation? You look at the data of the persons, huge amount of data comes, and based on that you run your algorithm, classification algorithm. So what is classification algorithm here, or clustering algorithm here? For example, Netflix sees that there are a lot of customers are watching different things, and it tries to, it runs an algorithm, and it tells that it divides the customers actually into groups. Now what Netflix sees that what is the common behavior in this group actually? If this is the common behavior in this group, let me design a web series or make a movie to cater to this requirement of this particular user. So this is a recommendation, and then send messages to this user that yes, at this point of time you have a movie or you have a serial like this, would you like to do that? So that hit ratio is more, because I'm getting a recommendation which I'm looking for. So there is a lot of science behind it, recommendation science behind it, and I think I have written all these things in the slide, what I'm telling. So you can see that there is a hyper, if you look at this last paragraph, companies such as Home Department, Lowe's, Netflix, etc. use hyper personalization technique. What is hyper personalization technique? They look at people who are like me in my choices and what they are doing, and based on that they offer me. For example, today if I do something, they know that okay, this guy is friend of so many people, and they also may like this particular product. Let us give this as a recommendation to them. So this is called hyper personalization. That means each person's information is stored, and based on that abstraction they recommend to others. They don't have my data as such, but they have the data about my friends. So if they know that they are my friends and their choices are that choice will be recommended to me. This is called collaborative filtering and all that stuff. Okay, classification and behavior analysis. Classification I've already told you. Let me talk about what is behavior analysis. Sentiments, right? When I'm posting in my Twitter, when I'm posting in my Facebook, so from that you can find out what is my sentiment, whether I'm angry, whether I'm happy, whether I'm emotional. So based on, so they do that behavioral analysis. There is a technique called WADER, the Valence Ever Dictionary for Sentiment Analysis, etc. What that when that dictionary does, it has a word, English word, and that English word that attach a value, whether it is a positive sentiment, whether it is a negative sentiment, or whether it is a neutral sentiment. For example, word happy is definitely positive sentiment, but I'm not happy about it is not a positive sentiment, it's a negative sentiment. Similarly, I am feeling thrilled. Thrill is a positive sentiment. Sad is a negative sentiment. So there are certain things which are completely negative. There are certain things which are completely positive. That means they have a scale actually. So in a 10-point scale, they say that happy is 8, good is 7, and fantastic is 10. So this is how they have leveled it over a period of time. That means they have taken Twitter data, etc., analyzed them for years together, and then they came out with a statistic that these words have a positive sentiment with a score of this, these words have a negative sentiment with a score of this, and these words are neutral sentiment. Now, when I type a Twitter or Facebook or something like that, the data science, the data model behind that tries to predict what is my mood. So depending on my sentiment, depending on my behavior, they try to take some actions actually. This guy is angry, so they will not ask you to buy any product about that. So this is how they do this actually. So sentiment analysis and behavior analysis is also important. Now I will go to certain application domains, banking and finance. Let me read it actually. So there are many application domains. They are there almost in every town. But if you look at application domains which are using data science to the maximum, one is called banking and finances. So with data science, banks can manage their resources efficiently. Banks can make smarter decisions through fraud detection. I told you credit card fraud detection, etc. Management of customer data, risk modeling. You know, when you apply for a loan, the banks calculate a risk for that, and based on how much risk is involved in financing you, they decide the interest rate. They decide whether they will sanction the loan or not. So that risk model, that crystal rating, right? You have a credit card rating and credit worthy rating, etc. All those things run on data science actually. Real-time predictive analysis, customer segmentation. They say they are good customer, bad customer, very high-valued customer, important customer, VIP customer. So they do that customer segmentation without your knowledge, because the way you pay your bills, the way you pay your EMIs, etc. Now, if you detect a fraud, bank allow the companies to detect the fraud that involve credit card, insurance, accounting, etc. Banks have the ability to risk modeling through data science, through which they can assess the overall performances. In real time, banks use machine learning algorithms to improve the analytical strategies. That is one way. Manufacturing, in fact, that's very important these days actually. People call it the industrial Internet of Things, IIoT. Industry 4.0, that's a next level of industry. You know, industry in the industrial revolution, 1.0, 2.0, 3.0, now it is 4.0. It's not autonomous, it is internet sensor-based autonomous actually. So all these manufacturings are now Internet of Things enabled, sensor enabled. So the data science has enabled the companies to predict potential problems, monitor systems, energy consumption, analyze the continuous stream of data, and all these things are possible. What is, I think in the last line, I have taken about the reinforcement learning. I'll tell you one line about that reinforcement learning, and you can read more about it. There are so much modes of learning. What is reinforcement learning in this case? What I'm trying to say, for example, I look at some data, I take a decision, but I will not be able to take the decision and know that whether this decision is correct, good or not at this point itself. For example, let's say somebody is playing chess. With one move, you cannot say whether it's a good move or a bad move. For example, I move the soldier one step ahead. You cannot say whether it's a good move or bad move. But if you analyze a couple of moves further, for example, 3 or 4 moves after that, then you see that, oh, that was a bad move. I should not have done that. So this is called, that means what? That bad move should be negative. I mean, you should not give more importance to that. So there is a question of penalty and reward. What is penalty? If you have done some bad moves, you should that move should be associated with a penalty. If you have done some good moves, that move should be associated with a reward. So you learn that in that way. So how do you learn? I learn in a way that if I make some decisions over a period of time, if that decision come out to be good, then I reward those decisions. And if that decision is bad, came out to be bad, I penalty that decisions and then do the learning again. So that what happens is that basically you start. So what is this? Why it is different and why I took some time to explain this? Because mostly people do research in, I give a record and then there is a level, good or bad or some output is there. But here I'm talking about that a series of records, then only you can tell whether it is a good or not. So in that case, you have to go back and do that. So reinforcement means you come back, do the learning again, come back, do the learning again, either give reward or penalty, and then the system becomes robust. So that is how and this is being done in manufacturing very, very, nicely. People do that, come back to the manufacturing process, revise the manufacturing process so that it becomes robust, reliable. Transportation, I think everywhere it is used actually, transportation. So transportation industry completely uses data sciences. Uber uses data science to the maximum. Ola uses data science to the maximum. So what happens actually, I'll tell you one thing. It uses so much of data about the customer to predict a price. If you know how Uber, Ola predicts the price actually, they give you the price actually. There's a lot of data science that is involved in that actually. They don't predict, they don't give you more, they don't give you less, and they try to optimize their profit. How it is being done? I tell you a very small thing actually. Even they analyze your battery, the energy remaining in your mobile phone to predict the price. If you have very less battery, they give you a very high price because they know that you don't have the choice of going to Ola and other things, and you will book quickly because you don't have a lot of battery left. So that is also one parameter. You can imagine that actually. So a lot of data they take from where you are coming, what is the time of coming, how many vehicles are available, how many times you have used it, hundreds of parameters they use it, and then they give you a price. You might have seen that you try to book, I try to book, we both get different prices because maybe your phone is less battery, my phone is more battery. I have used it in the past, you have not used it in the past. So many things are there in the transportation industry also, and particularly making the route, right? Shortest path route, and all these things are there that is used in the transportation industry. Healthcare, I think in the morning session also somebody just hinted about that. Image analysis, genetics and genomics, drug discovery, robotic-based drug delivery, predictive modeling for diagnosis, health bots. Health bots means they will try to virtual assistant. There is no doctor sitting there. It's a chatbot actually. You tell your problem, the chatbot will answer you. How the chatbot knows? He has not studied medicine, MBBS or MD, etc. Right? Because of the data. So much of data is fed to the chatbot. The chatbot is trained, and now the chatbot is able to tell you that if you give me your problems, I will be able to prescribe. So that's a virtual assistant, doctoral assistant, medical assistance provided to you. This is again, it's a good thing to do. You may not be able to do it. I tried it for homeopathic and other things. It is working little well, but I don't venture it to put it in the online because it's medical, right? Unless it is approved, you cannot do it. But this is possible. E-commerce, I don't want to tell you, Amazon, Flipkart, all these things, Walmart, all these people are doing it. They do, if you look at, let me read it. For identifying a potential customer, they do analysis. Use a predictive analysis for forecasting the goods and services. Optimizing their pricing structure. What should be the exact price that will attract the customer actually? If it is more, they will not be interested. If it is less, the business will suffer a loss. So they find that optimized threshold of the pricing. Backbone of the advanced recommendation system. They recommend actually, when you go to Amazon, you buy one, there are 5 different or 10 different products that are recommended out of millions of products actually. And that recommendation system is very, very advanced actually. Sentiment analysis, as I told you, you do the sentiment analysis and the feedback that provided by the customers to find out whether they are happy, they are not happy, they are bad, or all these things. I'll give you a very small example where even if you feel like happy, right? So somebody said that it's an analysis, it's a case study. You listen to me. Somebody wrote a tweet to Indigo or any X Airlines that I was traveling with my luggage from Calcutta to Bombay, but you see the airline delivered me at Bombay airport, my luggage is at Delhi airport. It's a fantastic service which they gave, delivering simultaneously my luggage and me at 2 different cities. But this is a very bad review. But it is very difficult for the data science people to find out that it's a bad review or good review, because you see everything is fantastic, good, excellent. All those words are used, but at the end the sentiment is bad. He is not very happy that his luggage went to Delhi and he came to Bombay. So these kind of analysis people are working on it, and then miles to go actually. This is one interesting thing because in our university we had a visitor called Raj Bhatnagar. He is from United States. And he was involved in this project. So he told us about the data science used in the political campaign in the US. He was in the team of Obama, Barack Obama, who was the ex-president of the United States, who won the election in 2008 and 2012. They did this data analysis. They have all the data about every citizen actually. So every citizen there is almost in the Facebook, Twitter, etc. So they have analyzed the data. I repeat, they have analyzed the data about all the voters there in their Twitter, Facebook, etc., and found out that this particular person is going to vote for either Republican candidate or Democratic candidate if he comes to vote. So what they did, they found out almost 70 to 80% of the voters. They found out that 70 to 80%, I repeat, India it is very difficult, but in US, they profiled 70 to 80% of the voters based on their social media profile, based on their phone calls, etc., and determined that if this guy is going to potential voter for Republican Party or Democratic Party. And then they gave this list to the Obama election campaign people. They ensured that the people who are supposed to vote for them, they kind of approached them, they kind of persuaded them to come for voting. That's very important. If you know that this guy, if he comes to vote, he will vote for me, it's better you campaign. You don't have to say that you vote for me. You just see that he's coming to vote. Because you know that if he's coming to vote, he's going to vote for this particular party. Obama campaign did this exercise in 2008 and 2012. And that's where I say that data science people, very, very interestingly, they found out that these people are going to vote, and that was a successful campaign. So that's what I'm saying. The data science campaign, political campaign, and everything is there actually, right? Data science has kind of entered into all possible domains: political, economics, medical, business, science, whatnot. So similarly, data science case study of Internet of Things actually. So Internet of Things generates a lot of data. Sensors generate a lot of data, and that data actually gives you a lot of information. And what do you do with that actually? So that is very important actually. So I am trying to tell you that it's all lot of applications are there, etc. And with this, I think I'll just tell you a couple of applications that we have done in our lab, and then they are also published in the paper. What is soft sensing? Soft sensing means if you have a sensor, it will collect the data. But suppose you don't have a sensor, or the sensor is very costly, or the sensor is not available, or the sensor cannot be deployed because the environment there is very harsh. We try to replace it with a software. So what is the software? The software is basically the data science based model. So we take that sensor, collect the data in various possible environments, and then we find that there is a relationship between this sensor and the other sensor data. Then I remove this sensor. Depending on the other sensor data, I predict this sensor. For example, if you say that if you know my marks in math 1, math 2, let's say English, and then logic and all these things, probably you can also predict what will be my mark in the other subject. For example, science. Now, because if he is good in math 1, if he's good in calculus, if he is good in geometry, if he is good in trigonometry, if he is good in let's say logic, if he is good in this, he will be also good in sciences actually. So that relationship, if you have found out, you can predict that okay, this guy is expected to score between 75 to 80 in science also. Now, science teacher may not evaluate it, or suppose that paper is lost, somewhere the paper could not be given, the paper is lost, or because of online something has happened. You can predict what will be the data based on some scientific study, and this mark can be awarded to you. So this is called a software-based sensing, software-based estimation. And what we did, so this is what is the problem with the sensors actually. There are a lot of problems with sensors. They are not very accurate. Sometimes you cannot get it in the market. Sometimes they are very costly. Sometimes they are not very reliable. Sometimes there is a lot of drift. They are not correct because, today it will give some value. About the blood pressure sensors, etc. Right? You have to measure 3 times to get the correct one. So there are a lot of things like that. So soft sensor is an alternate. What is a soft sensor? The term soft sensor is a combination of the word software, because the model are developed using our computer program, and sensors, which are actually hardware, because these models are providing similar information as hardware sensor. That's why we call it the soft sensor. So soft sensors are also sometimes known as virtual sensors. That's it. Now look at this. In many cases, what happens, I tell you, look at this second line actually. This difficult to measure variables. Sometimes you will not be able to measure certain types of variables because of the sensors are not available, very costly, cannot be measured, or sometimes they are faulty. They are also referred to as dependent variable. But what you do is that this difficult to measure variable, I will try to predict using easy to measure variables. So some variables we have measured, and based on that variable, I will try to predict what is the difficult to measure variable. I will not use that. For example, if you know my blood pressure, if you know my blood sugar, if you know my heartbeat, if you know my ECG, probably you will be able to predict some other body parameter. And that parameter, that sensor is not there. So what you do is that you will take these parameters, develop a function, and that function will give you the other value. So this function is actually a soft sensor. So that mathematical model is a soft sensor actually. So the easy to measure variables are referred to as independent variables. Independent means they are not influenced, but these independent variables with a function will define the dependent variable. So what is a data-driven software sensing design model? You specify the model application. For example, I want to develop a soft sensor for my heartbeat. Now that's by specifying model application. Now I get data about my other body parameters like temperature and blah blah blah, all other body parameters, and I also measure my heartbeat, right? And then I create a data. Now my heartbeat becomes the dependent variable, that is y, and my other parameters are x1, x2, x3, x4, x5 are becoming the independent variables. What I have to do is that I have to find out that f, that function, that model, that function of x1, x2, x3, x4, x5, etc. is equal to y. But that function is not known. And the function, I will use data science techniques to find out the function. And then once I know the function, I don't have to have a y sensor. I don't need a y sensor. Give me x1, x2, x3, x4, x5, I will be able to predict y. So this has two phased applications. One, if you don't have a sensor for y, you can replace it with this function, number one. Number two, which is more important, is that even if you have a sensor for y, sensors are hardware, they may fail, etc. This software can validate that hardware sensor. That means the software will predict one value, the hardware will measure one value, and then you can find out that if the difference is not that much, then the hardware sensor is working properly. That's how the thing is there. So what we have done, I'll just tell you one simple application here. We have been working on water quality monitoring and for last almost 8 to 10 years. And water quality monitoring requires some 600 to 700 parameters actually. But there are some important parameters like chemical oxygen on demand, biological oxygen on demand, chlorine, total phosphorus. These are all very hard to measure online because the COD, BOD, etc. they require 5 days of culture of the water to know the exact value. So online sensors are not there. Even if they are there are one sensor is there for COD, which cost me around 30 lakh rupees. So we thought that but we found that they are dependent on certain other parameters like temperature of the water, pH value of the water, dissolved oxygen component of the water, nitrogen content in the water. So if you know those values, probably we'll be able to predict the COD value using a mathematical model. So that is what exactly the problem is. So what you did, I mean, that's what I said, COD is chemical oxygen on demand. That is the COD. So we wanted to predict COD because COD sensors are not available. Even if they are available, they are very costly. It takes a lot of time. So online COD monitoring is not possible. So we thought we will develop a soft sensor for that. So what we did, we collected the data from the water bodies. If you look at this sensor layer, actually, we collected the data from the water bodies. You measured the COD. I mean, we conducted the experiment in the laboratory, the chemistry laboratory, environmental science laboratory, etc., to get what is the actual COD value. So we collected all the sensor values, that is x1, x2, x3, x4, x5, measured the y value in the laboratory and put it there. So now we know that x1, x2, x3, x4, x5, these are the like temperature, pH, dissolved oxygen, turbidity. So these are the parameters which I can measure. Y, that is the COD, I cannot measure. So I did it in the laboratory. I put it there. Then I trained my model. I collected some 1,000 samples and trained my model. So these physical sensors, we collected the data and look at the third column actually, the edge layer. In the edge layer means that Internet of Things, it collects the data, that is the data acquisition, and then with the live prediction. How do you do the live prediction of COD? There is no sensor. How do I do it? I use the mathematical model to predict the COD and using the data science technique actually. So this is how we did it. I mean, if you look at this is a buoy which is there in the pond in the institute, and there is a map here, the Ganga river data actually. We did it in both cases actually, because some reviewers question that you did your own experiment, how do you know? So there are two experiments. One is experiment in the institute pond, and the another institute is that from the website when the Ganga water mission, when the Ganga, that Kumbh Mela was going on, and they were publishing that data, water quality data online, and we downloaded from that website, and there they were also predicting COD, BOD, etc. So we took it out. So we took x1 to x10. These are the parameters. COD is another parameter which we could not measure, so we put it separately. And similarly, we did it in the experiment, and we conducted the data science research. So if you look at this, we look at the left side table actually. We conducted DO. DO stands for dissolved oxygen, pH, whether acidic or alkaline, temperature, ammonia content, total solid, suspended solid, turbidity, nitrate content, then water level at what, whether too much of water is there or less water is there, then TOC, total organic carbon, and then COD. So out of this actually COD, that the last parameter, if you look at the table, the last row, we took it as a Y. All other parameter we took as X1, X2, X3, X4 up to X8. So then we found out what is the relationship between the columns. That means how much DO is related to COD, how much pH is related to COD. So we put the covariance matrix on the right hand side. So we found that all those parameters are not important actually. 5 parameters are enough to predict COD with an accuracy of almost 95 to 96% actually. So after we predicted this actually, if you look at this, what I want to say is this. We have found that only these parameters, ammonia, total suspended solid, dissolved oxygen, pH, and these 4-5 parameters, 1, 2, 3, 4 parameters are good enough to predict the soft sensor or softer equivalent sensor for the COD, which we don't have. Now, if you look at this, I don't know whether you will be able to see it or not. Just a minute. Now look at this. This is the actual value of the COD, which is actually measured, and this is the estimated COD according to our model. Now we have taken around some 791, some 800 samples, and we have cleaned the data. So some 9 samples are gone. And look at this actually, if you can predict, it's almost same. I mean, this figure is not that good, but let me see. If you look at this figure, yeah, look at this. Look at this. So if you look at this, I took some samples actually. If you look at this, almost the blue and the red, they are actually predicted and the estimated value, and they are almost same. There is not much of a difference. Now you remember, I was telling you that this output is not this actual sensor output. This output is the data science, the soft sensor output, and the actual sensor output we have already observed in the lab, and they are almost same. So you don't have to go to the lab actually. That's what you try to do. So this paper is published in IEEE Sensors. I mean, some of you might be knowing that IEEE Sensors is a very prestigious journal. So development of chemical oxygen on demand using soft sensor. The soft sensor is basically the data science approach actually, using IoT and all that. The exactly same thing we did. So this is published in IEEE Sensors journal. Exactly same thing, almost same thing we did, but the technology was different, the data is different. This is called biological oxygen on demand. That is chemical oxygen on demand. This is biological oxygen on demand. Same thing, almost same technique, but the techniques are different. So here also we have used the data of both this Ganga river and all these things. We collected dissolved oxygen, temperature, pH, conductivity, oxygen reduction potential, turbidity, etc. And BOD we considered measured in the laboratory, and other sensors we collected the data. We applied the sensors and collected the data. And remember here, the parameter that influences COD is different from the parameter that influences the BOD. And you know, some of you who are doing data science research, we talk about that, right? We talked about linear regression, we talked about neural network, we talked about SBM, we talked about instant-based classification, K-star, random forest algorithm, random tree algorithm, and hybrid of that. And you know, all these things we tried actually, and the error is, look at the error actually. Look at the 1, 2, 3, 4, the fourth column. The fourth column says that the error is root mean square error is only 0.39, 0.29, 0.01. That means what? That means the prediction using these techniques and the data that you have used gives me almost accurate result as per the hardware sensor. And what is the advantage of that? You don't need a hardware sensor now. My soft sensor, my data science research is able to tell me what I'm trying to do. So if you look at this actually, the actual value is 1.218. We predicted to be 1.218. So there is no error. Actual value is 1.108. We predicted to be 1.107. I mean, it's almost nothing. So there is only one case, probably this one, 7th one, the 0.609 is the actual value. We predicted to be 0.801. Excepting that, almost all of them are accurate up to 3 decimal places or 2 decimal places at least. So that's the power of data science research and the model algorithms, etc. So if you have data, you can take that actually. So same thing we tried with the Ganga data also, as I told you, the one which you did in our institute and the other one we downloaded from the Ganga river data set, did the same thing, and we almost got the same result. In the Ganga also, the actual value is BOD value is 2.52. We predicted to be 2.53. Actual value is 2.52. We predicted to be 2.46. 2.2, 2.3, 30, 30. So almost same thing. Our prediction is almost same. Now look at this. The actual value, they got it after 3 days of laboratory experiment, but we predicted online immediately, right? That's the approach here. So this also is, I think it's also published in a very prestigious journal called Springer Compilation Intelligent Systems. So, now I'll try to stop here. I don't want to discuss much more than that. So the whole idea is that in the data science research, people do two things actually, and try to listen to me. So I think let me complete this. We have also done the work on intelligent sensor network, but this is also based on the same thing. What we did, I'll tell you this same thing actually, because I don't have enough time. What we did is we tried to use the ultrasonic sensor measurement system for accurate water level monitoring with data science technology actually, with all this machine learning technology actually. So what you did, people use these things, but they found it 18% error, 20% error in the actual measurement. Why? Because the sensors are like that. When the environment changes, the sensor measurement parameters changes, and they don't allow the sensors to measure it accurately. So what happens is that we try to compensate it. We designed a software data science based model, because say for example, let me tell you, the ultrasonic sensor sends a ultrasonic wave, it gets reflected, and you measure the time of flight, that means the return time, and then based on that, that the ultrasonic wave travels at a rate of 331 meters per second, that is the speed, and based on the time you can measure what is the distance, right? And you divide by 2, it measures the distance. But what we know, the physics people know, but that cannot be modeled here, is that the ultrasonic sound speed is highly dependent on the environmental temperature, humidity, and the other gases present in the environment. So that means if the speed what you took to be 531, or what you assume to be 531 meters per second, varies from 480 to almost 580, 590 in the different temperature and humidity zone. That means what? Your speed can be 480, but you are assuming it to be 531. Your speed can be 580, but you are assuming to be 531. That's where the error comes. Because if the speed is more, the return time flight will be less, and you feel that the distance is less. If the speed is less, the return time will be more, and you feel that the distance is more. So there is an error of almost 18% in the actual measurement. That means if you measure, let's say 5 meters, it was almost showing you 6 meters. So that's the level of error. So we want an accurate level monitoring. Use all these techniques, whatever we have discussed. We took the data, so much of data, what is the actual data, what is the measured data, etc. Then we trained the data and compared. And this is published in IEEE Transactions on Instruments and Measurements. And I mean, it's not a great thing, but still we could do it, conducted the experiment, collected the data. So that's where I say that in data science research, there are two ways of doing. One is that you download the data from different sources, like you go to the UCI repository, you go to different Google data search, etc., and run your algorithms, run your methods, and publish a paper. That's one way of doing things. The other thing is that, okay, that's good. I'm not saying that's bad. The other thing is that create your own data, right? How do you create your own data? Collect the data, collect from friends, collect from students, collect from society, collect your own data, and then collect the UCI repository data, download the data from the internet, etc. Then run your algorithms or develop your algorithms and test it both from the internet data and on your own generated data. And that's where the level of publication differs actually. If you do this, for example, as I told you, we did the experiment in our local institute in the pond and etc. We also downloaded the data from the Ganga River data, which the government site provides us. And we compared the data or executed the algorithm in both the data set and say that, look, in both cases, I'm getting the same result. So that's one way of doing things. So I think that's how it is. And the last one I would like to say, I have extended my time. There is one logic is that you see, basically I'm working on sensor network and everything. So what happens is that there is a sensor node that is deployed there with a lot of sensors, and that data continuously sends data to this server. That particular node continuously sends the data to this server. The problem is that if it is battery powered, the most of the energy is used for the communication, not for the processing actually. So if you keep continuously sending the data to the server, your battery will dry soon and the node dies. What we thought, can we use this data science principle and increase the lifetime? How it is possible? We collected the data at both the level, at the edge level, that means at the point of data collection, and at the server level. Based on the previous data, we fit the linear regression, multilinear regression, multiple modeling, etc., and then found out that what is the next data. That means if I have 1, 2, 3, 4, 5 up to ith time, then I tried to predict what will be the data in the i+1th time. How? Just fitted a model to the all the I data, and we predicted what is the i+1. Then we checked what is the difference between I plus 1, actual I plus 1 and my predicted I plus 1. If they are not same, then I trained again, right? So after some time, I find that the training is good and it is almost working. Then what I do, I develop the model, I put the same model in the server, I put the same model in the Internet of Things node at the point of measurement. The node will collect the data from the sensors, will also run the model to find out what is the estimated value. If the value between the estimated value and the actual observed value is not very much different or not is almost same, then it did not send the data to the server. Then how the server estimates the value? The server has the same model. So the server take the previous I values, predict the I plus 1 value and create a record in the database. That means there is no communication between the node at the end and this server. And if the communication is not there, energy is not there. That's what we did it here actually. And so you will be surprised that I mean, I tell you, the surprise that almost 90% of the time, 89.63% of the time, I'm able to predict the data accurately in the server without getting the data from the node. So that's very important actually, right? So we are able to predict the model 90% of the time. That means the 90% of the communication cost is reduced, and your at least, I mean, I tell you, at least your lifetime of the sensor node increases by 9 times. That's the power of machine learning and the model here. So again, this is again published in Springer Wireless Personal Communication Journal and all that. So we used all these techniques that whatever we have discussed, and there is a site called WSM System for Water Quality Monitoring. We got a project from DST. We did all these things. We tried to predict all these values. Some values we observed, some values we have predicted. We have deployed at different places in Hyderabad. We found these values. These are all in the Google map actually, right? You click on that particular node, you get the values. Some values are not there. They are predicted through soft sensor and all these things. And these are some of the students who worked on there to deploy them at different places. So thank you. I think I'm sorry I exceeded time by almost 10-15 minutes. If you have any questions, you can reach out to me through mail, WhatsApp, whatever you like. Thank you very much.
Thank you, sir. Thanks for this wonderful and informative session. So you have explained about the data science and its applications and the future directions deeply as possible.
Yeah.
And participants, it is your time now. So if you have any queries or regarding the session, you can ask, and you can also share the valuable feedbacks.
I'll just take one question. I think somebody is asking about is there any advancement in dimension reduction methods? Presently, I'm using PCA. I think Dr. K. Ramakrishnan. Sir, even in PCA, people say that the principal component analysis is already there and it is not, I mean, it's almost saturated. No. How do you use PCA? PCA is basically principal component analysis, but to calculate PCA, principal component analysis, there are hundreds of methods. So don't worry about only PCA, PCA1, PCA2, PCA K. K is very large. So there are a lot of PCA techniques available and you can try them. There are independent component analysis, there are wavelet transformation. There are so many dimension reduction problems. And very recently, people have used deep learning also for dimension reduction problem itself. People have used deep learning. People have used other machine learning tools. And you can find out. There are so many techniques actually. I don't want to go, but just because I picked up this question to tell you that PCA is not one technique. PCA is a number of techniques. How you do the PCA, there are a lot of people who are doing with PCA with PSO, right? So they use PCA optimization technique to find out the right kind of component actually. What component? Principal component analysis means you have to find out the components and then you find out what are the attributes that are contributing to those components actually. For that, people have used a lot of optimization techniques also. So Ramakrishna, what I'm trying to say that don't worry about only PCA. PCA has so many variants and try to look at them. Independent component analysis, ICA also you can look at them. Yeah. Anything else? Okay, good.
Participants, if you have any doubts, please unmute and ask. I think it is a lunchtime maybe.
Yeah.
Yes,
It's lunchtime, so people might have gone, but that's okay. They can write to me whenever they feel like. Oh, somebody is asking Aruna Gawade, sir, any free tool to do sensor sync related experiments? See, madam, free tool in the sense ki if you have this Weka, MATLAB and other things, these tools only you have used. Python anyway is free, so PyTorch and all that. But the collection of the data is not free actually, right? You have developed models, you have to develop nodes to collect the data. But if you want to use the data which is already collected and there in some repository, etc., you can take that data, run your applications on Python and all that. And there are a lot of other tools. I think Python is good. You don't have to look for other tools actually. PyTorch, Python, they are good actually. That Panda framework is pretty good. So you try to do that. Yeah.
So, Manas, continue.
Okay, participants, if you don't have any further queries, we can wind up the session. So now I would like to invite Dr. Kumar V, the organizer of this event, to deliver the vote of thanks. Sir.
Okay. Professor Siba K, Professor of Computer Science at Artificial Intelligence Lab, School of Information, School of Computer and Information Sciences, University of Hyderabad, delivered a very wonderful lecture on data sciences basics, applications and challenges. It's really interesting, and most of the people enjoyed. By seeing their queries, we can observe that they understand the concepts and they enjoy the session. And sir covered most of the things. Sir, I found very one interesting thing: data collection examples. So each and every moment of the life, data is generating and collecting and storing somewhere, while purchasing, while booking, while applying, even while walking also the data is recording and storing. So each and every moment of the life, data is generating and recording somewhere. Yes, are also given a good real-time applications related to data sciences like banking, transportation, healthcare, e-commerce, political campaign challenges, and are also given explain the research going on in their laboratories. So really, it's a very wonderful session, sir. We are happy with your talk. So on behalf of the Department of Computer Science, Central University of Kerala, on behalf of the participants of this program, and on behalf of my personal, very heartfelt thank you for accepting our invitation and delivering a wonderful lecture, sir.
Thank you.
We hope your support in the future also, sir. Thank you very much.
Where is this university exactly? But I mean, just asking.
It is near to Mangalore, sir. Mangalore, you know.
Oh, near Mangalore?
Yeah.
Oh,
From
I went to
Bangalore.
Bangalore University, I think 3 months back for some NAC accreditation and all that.
Okay,
So,
sir, okay.
oh, it's very close there. Okay.
Yeah, sir. 1.5 hour journey from Mangalore airport.
Oh, very good. So I was there in Mangalore for a couple of months back as a NAC PhD member.
Yes, sir. It's a new university, sir. 11 years old.
No, I know all centers. I know.
Yes, sir.
Okay, good.
Anyway, thank you, sir. Thank you very much.
Thank you. If you are coming to Hyderabad, you can come to our lab, visit our lab and see.
Yes, sir. Sure,
okay.
Sir.
Good.
Thank you.
Thank you all. Have a good day. I may join some of other sessions also.
Yes, sir. Sure. Thank you.
Thank you.
Thank you, sir.
Thank you, sir. Participants, please note our next session will start on 2:30 sharp. So please make sure about your availability. Okay,
and
sir, can we wind up?
Also, one more thing. Participants, please join on time. I observed participants are joining continuously from beginning to the ending. So don't do that. You start at the beginning of the program itself, and we are monitoring your attendance through the Google Meet. Okay. So there is no separate Google form. So Google Meet attendance extension is there, so it will record each and every time. Whatever the time you are recording and exiting, everything it will be recorded. So there is no separate attendance. Okay, please cooperate and join in time. Thank you. We'll meet sharply at 2:30. Before 5 minutes or 10 minutes, this will be open. Platform will open to join. Okay. Thank you all.
Okay, sir. Thank you.
Okay.